string n, let's say, if it's a finite language. And then you might have string 2, string 1, string 2, string 2, string 2, string 3, string 2, string 4, string 2, dot, 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 string 2, string n, and so on. And then all possible strings with three well, the concatenations type 3, where you have 3 strings concatenated from your language, and so on and so on. Right, up to k strings concatenated, and k can go on, unless you're told otherwise. As far as I can see, k just goes on forever. So a star is just an infinite set, a countably infinite set. Okay. So a bit of revision of what star does. Okay. Alright, so we're trying to find an automaton that recognizes a star, or A1 star, our one language. So you star that language, and we have to find a machine that recognizes it. So how to do that? Alright, well, so the basic idea again, there's always some creative idea that's the core, the heart of the proof. When you think of it, you go, aha! Like you found the essential idea to making the proof successful. And the idea is the following. Now, if you've got, let's say you've got like a k concatenation. So, in other words, you've got a concatenation of k strings from your language, one after the other. And that each string could be any string in that language, but you've got k of them, just concatenate one after the other. So you're just going to need one machine as a part in your bigger machine. So your bigger machine, again, we'll just call it big N. Okay, and this time we only have one part. We'll call it N1, which itself is an NFA. Okay, and the basic idea is that you send in your string into N1, and if you end up in a detect in an accept state in your N1 that's a part of big N, well then you use the arrow, the eta arrow, to loop back to the start state of N1. Okay, and you can keep doing this as many times as you need, right? So that's the core idea. So you use the eta arrows, and you loop back, like you jump back, if you like, from the start state, from an accept state of N1 to the start state of N1, and then you go looking for like the second string in your concatenation, and if you find it, well then you loop back and look for the third one, and so on, right? So so the essential idea is forget about this for the moment. This is a complication, but think of this, right? So you start state here. You end up in an accept state, let's say. So you found let's say the first string in your concatenation. Well then you, under eta arrow, you come back immediately to the start state of your N1. This is your N1, okay? And it's just one part. And there's only one part, well, effectively, in your bigger machine N, okay? So that's sort of the essential idea. Now there is one little complication, and that is A star, or A1 star, includes the empty string, eta, right? So hence this little piece here is sort of a complication, and it allows you to it allows you to detect the case when your input string, your concatenated input string, is in fact empty. So if your input is eta, then this will allow for it. So yes, it's just a complication, a special case. So what you do is you make you have a, well, one idea, and it's a bad idea, but one idea would just be to have this input string here of N1 be an accept state. So in other words, put a double circle it. But if you do that, that might seem plausible. But if you do that, there are unwanted side effects. Things happen that you don't want to happen. So another way is to do this, is to create another start state outside N1 here, and make it an accept state for N. And that's why you've got two circles here. And it's, this arrow here shows that it's the start state, but it's also an accept state. But it's outside N1. And by doing that, may not seem obvious, you have to think about it, but by doing that you avoid this, these unwanted side effects. And what does that mean? Well, you're accepting strings that you don't want. Well, that's all I'll say on that. Right? So you have this new start state with an eta link to the start state of N1, and that solves that unwanted side effect type problem. All right. Now. Well, I think we've pretty well done the proof idea. So the main idea is just one component N1, and then if you've read in the first string in your concatenation, so you're in an accept state, and we'll then use an eta arrow back to the start state, and then try again for the next string, the second string in your concatenation, and so on, the third string, the fourth string, and so on, as long as you need to go. Now, A star is an infinite set, right? So the number of concatenated strings in that language could be infinite, countably infinite, right? So you might have a finite number of strings, so you'd have to loop back like this finite number of times, but it could be a large number of times. Just a minute. There's my computer again. Alright, so...
A vast iris database.
Okay, now let's do the actual formal proof. So we need to, as usual, we need to find the, it's again a proof by construction, that's no surprise. So we have to find the formal description of this big N, so the usual 5 tuple. And we're going to use N1 as a component, as a part of the bigger machine, although it's not much bigger, right? There's only one part with this little complication here. Okay, so here's our formal specification for N1, which recognizes language A1, and then we have to construct, it's a proof by construction, the machine big N, and here's its specification, okay, and its job is to recognize a star, or A1 star. Okay? Remember that language, a starred language, is all possible concatenations of strings of that language. You could have like k strings concatenated, and k could go on as high as you like. So it's, A star is effectively an infinite language, countably infinite language. Okay. So we need to specify now what these are. So what's Q? Well, we only have one part, and that's N1, so it sort of seems reasonable that we'll have the states of this machine N1 plus this extra one, right? So call that state Q0. Okay, so that seems reasonable. That'll be the states of your whole machine N. Okay? Just the parts of the states of Q1 plus this extra state, this starting state that's exterior external to M1. Okay, so I'll just go straight on with the next session.